Hello grade 11s, great to be with you again. Today we're looking at the topic of intermolecular forces. Now intermolecular forces is a kind of a mixture between chemistry, but you also need to remember the topic of forces from your physics. So don't forget that. Let's go and have a look at exactly what we're going to be covering. So as I've said, our topic today is intermolecular forces. Just a little question about that. Inter. Remember, inter means between. So if we break it down, we'll recognize this is about forces that act between molecules. So molecular relates to molecules. And so we're asking about the type of forces that exist between molecules. This is what we're going to do. First thing we're going to do is we're going to compare intramolecular forces and intermolecular forces. Intra means inside, and inter means between. So we have to get those very clear, and we have to be very definite about those and understand where the different forces come from and try and explain them, because they'll have an influence on the physical properties of the things that we're looking at. And so that's the next thing we're going to do. We're going to identify different types of intermolecular forces. They're not all exactly the same, because the type of intramolecular force, or the type of chemical bonds, are not all the same, and that will influence the type of intermolecular force. And so then the last thing we're going to do, and we'll break this up, is we're going to identify the relationship between the state of substances and the intermolecular forces present. In that sense, we're going to look at physical properties and try and explain those physical properties in terms of what's happening at a microscopic level. And we'll use the different types of intermolecular forces to explain these very things. So let's get cracking, and let's get straight away. We're going to have a quick revision on matter and the different types of substances that you can find, and therefore the different types of chemical bonding that take place. We're going to just simply focus on pure substances and recognize that when we talk about pure substances, we recognize there are two main groups: elements and compounds. Now, when we focus on elements, we recognize within the elements, we can break them roughly into two groups: the metals and the non-metals. All of these elements have a basic building block of the atom. So the metals and the non-metals are basically made up of atoms. Atoms are the simplest form of an element. In that sense, what we recognize, they're the building block of all matter. We need to understand that we need to link the word element as a macroscopic view. When we can say we look at a steel nail, we recognize, or an iron nail, we recognize that iron is made up of tiny little atoms that make up that element. So that subsection, the very small particle that makes up, is called an atom. But we recognize also that atoms can combine. We've spoken about chemical bonding to show how atoms can combine to form molecules and to form bigger structures like crystal lattices. And we recognize even in metals that these atoms combine to form a metallic lattice. Now, what we're interested in today is to look specifically at where molecules occur. Now, what is a molecule? Let's go and have a check on this, because in terms of molecules, we need to recognize that we'll find molecules in two places. We'll find molecules, first of all, amongst the non-metals, where two or more atoms of the same atoms combined. So with non-metals, what we sometimes find, and I'll give you some examples, the non-metals, two or more non-metals may combine to give you molecules. So two or more non-metal atoms combine to give you a molecule. Example, we would have something like oxygen Now, oxygen is a diatomic gas. That means that there are 2 oxygen atoms in every 1 molecule of oxygen. So if you got that picture, nonmetals can combine to form molecules. There are some special nonmetals that are found in group 18 of the periodic table, right at the end. They're very stable. They don't combine to form compounds at all. They're known as the noble gases. An example of a noble gas is helium. It is an atom that exists on its own. So helium, symbol He, exists as a molecule. And it's very happy being a molecule. In fact, we can see some of the properties of helium, both its chemical properties and its physical properties, because of what's happening between the molecules. It doesn't combine with anything. Now, what about the compounds? Let's break this down and recognize that compounds can have 2 different ways of forming. And it depends on what's involved. Ionic compounds, those form when we get a metal and a non-metal combining. And you will recall that the metal loses electrons to become positively charged, the non-metal gains electrons to become negatively charged, and they're held together by forces of attraction. Those forces are electrostatic in nature, and so the positive will attract the negative, and they're very strong. Those are not the type of forces we're talking about now. Those are forces between ions. And ions aren't molecules, so be very careful about that. We will discuss that in a little bit more detail when we come to a fuller picture, but for the moment, please recognize we're not talking about ions. We're talking about where molecules exist. So where do molecules exist? We find them when there are covalent bonds. Remember, covalent means that there's a sharing of electrons. So when electrons are shared between 2 atoms, their orbitals overlap and they share an electron pair to form a bond or to form multiple bonds. We recognize this type of bonding is called covalent. Usually when we have covalent bonding, we can generalize and say covalent bonding produces molecules. And there are different types of covalent bonding. I want you to understand that very carefully because it's very, very important. And so I've illustrated that down below here. We share electrons, and sometimes we share them equally. So if we have equal sharing, then what will happen is that bonding pair, the force of attraction from the one atom to the other is the same. And so what we recognize, that pair of electrons is evenly distributed. There's not one side of the molecule that becomes charged with any small charge. However, when we get a big atom like chlorine and a small atom like hydrogen, then what happens is that hydrogen's electron gets pulled towards the chlorine side. And what we get is not an ion forming, but it's kind of half an ion. In this sense, we form one end as being a little negative and the other end being a little bit positive. And so we call that a polar molecule, where there's unequal sharing. Now you're going to say to me, but John, how do I know when it's unequal and when it's equal? Here's a rule of thumb. There are 2 things that you need to know. When it's the same atom binding together, joining together, bonding together, the intramolecular bond, the forces between those atoms are intra. When it's the same, the force on that paired electron, they're going to be equal because they're identical. There's a term that we've used, and we used it in our previous session on chemical bonding when we spoke about electronegativity number difference. That gives you a sense of how strongly the electrons are being pulled to one side or the other. When the electronegativity number difference is 0 or close to 0, less than 0.4, then we can say that the bond is nonpolar, that the electrons are equally distributed. So a nonpolar bond means that there are equal sharing of electrons. One side of the molecule is going to not be different to another. And I think that's important to take note of. So I want to note this. In a nonpolar bond, what generally happens is we get equal sharing, and because it's equal sharing, the molecule is known as a nonpolar molecule. And if we have to draw it, we would represent something like that, and we recognize that wherever we are, there's an equal distribution of electrons. So depending on the size of the molecule, obviously the positives and negatives are going to be the same. There are going to be positives in each of the nuclei, and they're going to cancel out with the number of electrons. I haven't drawn them the same here, but what I'm illustrating is that these electrons are spread equally. Electrons are evenly spread, even spread. Okay, make sure you've got a very clear understanding of that. Nonpolar molecule comes from a nonpolar bond, and that means that there's an even spread of electrons around the surface of this molecule. Now, what happens with a not a nonpolar bond, but a polar covalent bond? Here's the interesting one. I'll give you the example earlier when we have a polar covalent bond. Then what we're going to find is there's unequal sharing. And because there's unequal sharing, what we find is that one end is different to the other. So one end of the molecule may be different to the other end. Here's the example of that particular case. So if we take the example that I spoke about, hydrogen chloride, hydrogen is a very small atom, and chlorine is a very large atom. When they overlap, you've got a difference in size, and you've also got a difference in electronegativity. The electronegativity is the ability of a non-metal or a metal to attract a bonding pair. So which one's going to pull harder? The chloride ion, or the chlorine atom at this stage, wants the electron so it can become stable. The hydrogen's not too worried. It can exist without its pair of electrons. It can have them at a distance. The chlorine wants it close. It wants to get a full shell. And so what happens is that the electron pair, which I'm going to represent in a different color, I'm going to represent it as two little arrows, is pulled closer to the chloride side. And because it's pulled closer, what happens on the chloride side? This chloride side becomes a little bit negative. It's got more electrons than protons. Remember, in the chlorine atom, right in the nucleus there are a limited number of protons. In fact, there are only 17 protons. If we've got 17 protons, we've now got this extra electron that's spending more time. It's almost like having an extra electron with that bonding pair being pulled in. Started with 17 protons, 17 electrons. Now it's picked up the extra little bit from the hydrogen because that bonding pair is still a little bit close to the hydrogen. It's not totally away from the hydrogen. It's not an ion. So we say that it becomes a little bit negative. And we draw this silly little D symbol represent it as a delta, and we say that's delta negative. And on the other side, the hydrogen's lost out a little bit, so we say this is delta positive. Now, when we get an example like that, one end is positive and the other end is negative, and we say we've got two poles. Now, the word pole is simply two opposites. If we recognize we've got a north pole and a south pole magnetically, they're different in their nature magnetically. Geographically, we've come to recognize there's a difference north and south. They're opposite ends of a big spectrum. So when we have the word pole, it just means two opposites. So here we say that this particular molecule has got two ends. It's got one end positive, one end negative. And so we say that this is a dipole. It's a dipole. One end positive, one end negative, and so we recognize it as a dipole. Now, please, I want you to pay careful attention here. You will have remembered from our session on chemical bonding that shape of a molecule is also an important criteria. And here is something that you've got to pay very careful attention to. When we have molecules that are linear and they're straight, one end's positive, the other end's negative, it's easy to see that the whole molecule, the bond is polar, covalent, unequal sharing of electrons, and because it's in a straight line, the molecule itself is a dipole. But that's not always the case. If it happens that a particular molecule is not linear like that, or even planar, what we'll find is something interesting. Let's have a look at it as a particular example. You will remember that we've discussed using a bonding model called VSEPR, which simply means valence shell electron pair repulsion. And what that's saying is that electrons in a particular molecule will repel each other, and they will try and arrange themselves in space as far away from each other as possible. And so if we look at this example of carbon with 4 hydrogens, and we simply drew it as simply as we could, we'd recognize we'd have something like that. But you know that's not the real shape of this molecule. This is the methane molecule. And we recognize methane doesn't have a bond angle of 90 degrees. It doesn't mean that the distance, the angle between this hydrogen, the carbon, and the hydrogen there is 90 degrees. It is much bigger. And the reason for that is that the molecule takes a 3-dimensional shape. And in fact, even though we draw it like this schematically, what we need to recognize is that molecules that form 4 bonds, they take the shape of a tetrahedral with an angle of 109.4 degrees between them. That's a very symmetrical shape. What you need to recognize now in terms of 3D symmetry is that even if I put something like carbon and hydrogen, where there's a slight difference of electronegativity between them, that what's going to happen in 3 dimensions, because of the symmetry of the molecule, they're going to cancel out. So it's possible, and that's the point I want to make, that this bond could be polar covalent. In this case, it's slightly polar covalent. So the bond can be polar covalent, but the molecule, because of its symmetry, the molecule is non-polar. Now, let me just say that again, and so that you've got it very clear. Even though the bond is unequal sharing of electrons, the electrons are pulled either in one direction. In this case, they'd be pulled to the more electronegative substance, which is carbon. And so the electrons would be pulled downwards. And the electrons for all the 4 would be pulled towards that. So the carbon would be slightly negative, whereas the hydrogens would be slightly positive. And we would think, we've got at one end positive. No, all the whole distribution, because it's over the total molecule, and because of symmetry, the forces kind of cancel each other out. The components of the forces cancel each other out. And so what we recognize is that the molecule is symmetrical, and because it's symmetrical, the molecule is nonpolar. And that's a very important thing to take note of. You've got to consider the shape of the molecule. If the molecule is not totally symmetrical, an example being water or ammonia, then we get a very strong relationship with polar molecules. Polar bond, polar molecule, because it's asymmetrical. So bear that in mind. Those are important points to take note of. Okay, I think we've covered enough on that particular introduction. What I want to move on to now is to mention the types of intermolecular forces. So when we take a look and we recognize molecules come in different types, then the types of forces must be different too. And that's exactly the point that we want to make. So I'm going to start with a particular type of intermolecular force, and we're going to expand as we go down. So the first one that we're going to look at is a dipole matching with another dipole. Where would we find this? Well, let me give you some examples. The first example was one that we've just done in terms of hydrogen chloride. Another example would be hydrogen sulfide. These are molecules in which one end is a dipole and the other end is, one end is positive, the other end is negative. So what does that look like when we put molecules together? So here's one molecule, here's another molecule. If this end is slightly positive and this end is slightly negative, then what you need to recognize is that as these molecules are moving around, that what's most likely to happen is that the negative end of the second molecule will be attracted to the positive end of the first molecule. And so there will be a force of attraction between these two ends. And I filled in that force as a dotted line. Remember, if these molecules are moving, this could just be a temporary interaction, depending on some other factors, which we will discuss. Forces will be attracted. They won't necessarily be permanent. They might be very temporary. As the molecules move from one place to another, if they're in a solid or in a liquid or in a gas, they certainly will be moving. In a solid, they will be vibrating, and we'll get a little bit of a stronger force. The molecules will be slightly closer together. One of the important factors here, when we say dipole, what we're recognizing is that the force is in a particular direction, but if another molecule comes in over here, for example, it doesn't have to follow a particular pattern. It doesn't need to be like a crystal lattice. We could have this one as delta negative being attracted over there as well. And if I just put in the pink line over here, we recognize that that's fine. It doesn't follow particular angles. Remember we said in the tetrahedral, 109,4 degrees has to be that, can't be anything else. We can identify that. In water, very specific angles within the molecule. Now, when we're talking about intermolecular forces, they can be fairly random, particularly in liquids and gases. They don't have to follow a particular angle. They can be in any direction, just depending on how the molecules collide with each other. Right, let's move on. That's the first one that I think that we need to deal with. The second one, that is probably also just as simple, is what happens when we've got a nonpolar molecule linking to a nonpolar molecule. Now, these ones, you would say, electrons equally distributed, we're not going to expect much to happen. And you would be absolutely right. These nonpolar interactions are very, very, very weak. And in fact, we will give a certain name to them. We will say that they are very temporary. They are temporary. And they are what we call an induced dipole. Now, the name given to these, they're sometimes known as London forces. After not the town London, but somebody called London, a scientist with a surname London, who postulated where they could have come from and their origin. The important points about them, they're temporary and they're induced. What does induced mean? Well, you might have come across the word, but I want to explain it in this context very carefully. So if we have a molecule and it's got an even distribution of electrons, and I do something, I bring another molecule close to it, moving rapidly towards it, then what's going to happen is it's going to have an effect at a distance. Remember, we've classified forces in different ways. We've said there are contact forces and there are non-contact forces. So here is another example. It's an electrostatic, non-contact force, molecule moving towards another one quite quickly. What's going to happen? The electrons that are evenly distributed are now suddenly upset by this approaching electric field. The electric field of the molecule approaching causes there to be an unequal distribution. And so let me try and show that to you in a little sketch, a little diagram. We'll do it like this. We'll say, here's a big molecule, and here's another big molecule, and the electrons originally were quite evenly spread across the surface of the molecule. Now I'm just going to put 6 or 8 little electrons. Let's call them the same. So we'll have them evenly distributed in that sort of fashion. So I move that one towards it. What do you think is going to happen? Well, let me redraw it, and let's just see exactly what's going to happen. As it gets closer, what we're going to see is the following pattern. This one is moving, so we say this one has a little bit of velocity. Then what's going to happen is this. I'm going to keep these ones in more or less their same positions, something like that, evenly spread. But on this side, all of these electrons that were sitting over here, and they were very comfortable sitting over there equally, they've suddenly got an approaching negative charge coming to take them. What happens when we get negatives moving towards negatives? Well, we know negatives and negatives don't like each other. They repel. Now, if this one's moving, it's got a little bit more momentum. So this molecule here with the electrons, all the electrons can do is they can run away. And that's exactly what happens. So this one now, just for a second, a split second or so, the electrons, not all of them, but a lot of them group towards the other side. And just in that moment, what happens is that this end becomes slightly negative. And because there's been a rush of electrons from one side across the surface to the other side, this end, where the electrons were, becomes slightly positive. Now what can you see? I hope you can see that there's a reaction. It's like dominoes falling over. What we've done is we've induced a dipole. It wasn't there to start with. It was just a temporary induced dipole. And what we recognize is that this dipole has been set up, and what does that do? It has an effect on these electrons. And the effect is to say, okay guys, we'd like to get a little bit closer. So those ones all rush towards that end as well. So some of these end up rushing towards this side, and this end now becomes slightly negative. And this end becomes slightly positive. And so here we've got a chain reaction within the molecule. It might just last for a second or two, and then they split apart. But the effect is that there have been these molecules are held together a little bit stronger than they would have been if that hadn't happened. This is known, as I said, as London forces. These ones, the dipole-dipole, were originally discovered by a man called van der Waal. And so in different textbooks, we recognize these as van der Waals forces. Van der Waals forces. However, over the years, there's been some discrepancy, and some texts refer to all intermolecular forces as van der Waals forces. I think it's important to make a distinguishing statement between dipole-dipole and the others of non-polar-non-polar, non-polar-non-polar, induced dipole, temporary dipole. Those are London forces, where all the others are generally known as van der Waals forces. Now, there's two other categories, and these don't occur very often, but I want to show them to you. And the first one I'm going to say is look at an iron dipole. Now, you can call or see what happens here. If we've got an ion, something like sodium, within a solution of water, so if we've got a water molecule, and I'm just going to represent the water molecule like that, and recognize that that is H2O. So what's going to happen if I put this positively charged ion and put it into water? There's the water. We recognize water is a polar molecule. It has a negative end, which we write as delta negative, and the positive end is on the hydrogen side, delta positive. Then can you see that what's likely to happen is if I take the positive ion, it's going to be surrounded by a whole lot of water molecules. And the water molecules are going to orientate themselves something like that, so that the negative ends of the water molecules, these being delta negative, are going to face inwards to the positive ion, and the delta positives are going to face outwards, and it's going to be that sort of effect. Now, this can happen in a non-polar situation as well. This is another example of van der Waals forces. So these ones would be quite strong, but if I have an ion, like a positive ion, in a non-polar solution, non-polar, so this is ion non-polar, these aren't going to be very strong at all. The positive ion is going to induce a charge around this one, and we're going to find the electrons gathering to that side, gathering to this side stronger, delta minus on this side, and more electrons are going to be on that side. This one's going to get a delta plus over there like that. These tend to be very weak. They tend to be very weak, and we don't come across them very often. So I'm going to just leave them like that. There is one last category of intermolecular forces that I must mention. These are a special type of dipole-dipole intermolecular forces. We give them a name, and the name is hydrogen bond. I'll tell you exactly why it is called like that as well. So the last type, these are known as hydrogen bonds. So hydrogen bonding, or hydrogen bonds, is a very important type of intermolecular force. Please note, this is intermolecular. It's not a true chemical bond. It's not between atoms, it's between molecules. And that's how you can tell that they're different. These are between dipoles and dipoles. It's a special case of van der Waals. But in this case, there are very strong dipoles and very strong dipoles. The examples that you need to know that there is hydrogen bonding in water, in H2O. There is hydrogen bonding in something called hydrogen fluoride, and there's hydrogen bonding in ammonia. There is also hydrogen bonding in your DNA and in other organic molecules that are really big. What do you notice about these three molecules? Well, you should recognize that in each case there is a hydrogen present. So you can't get hydrogen bonding without hydrogen being present, one hydrogen atom being present. The second characteristic is that the molecules are very strong dipoles. If you go and look at the electronegativity difference, you'll see that it's a particularly high electronegativity difference. And the second attribute that causes this very strong dipole to form is because of the shape of the molecules. Now, it was based on the shape and the strength of the interaction between these molecules that led scientists originally to think that these were a new type of chemical bond. And I'm going to illustrate this particularly with hydrogen fluoride. What we notice with hydrogen fluoride, very simple to see, that hydrogen fluoride is a molecule that is linear. But when you look at it in its various states, we could draw it like that. But what was noticeable when they did X-rays and they did all sorts of interaction with it to try and understand it, some people even thought that hydrogen fluoride existed in different forms. They said, no, you can get a molecule of HF and you can get a molecule of H2F2, and this one would be H3F3. And that's not true. That's not what we understand today. That's wrong. The reason is that this attraction that I've drawn here is actually a hydrogen bond. That is hydrogen bond. Now, what was the confusing bit was this was always at a particular angle. There was a set angle, and it made people think that this was strong enough to be a chemical bond. And in some cases, it's very close to being the same energy that breaks the hydrogen bond is very similar in energy that will break a chemical bond. But it's not a true chemical bond, because remember, a covalent bond is where there's an electron pair that is being shared. Here, it's just simply an electrostatic attraction between a negative end of a dipole and a positive end of a dipole. So please take note of that and don't get confused. Now, you know what? I think it's time to just take a breather. When we come back, we're going to take a look at some examples, and we're going to do a few more activities related to intermolecular forces. So don't go away, take a stretch, get your notes out and make sure that you're on top of all of this. And when we come back, we'll get into applications of this theory to solving some problems. We'll see you in a while. Welcome back from your break. Let's get straight into it. I hope you're getting the idea of where intermolecular forces, you've got it very clearly, they're between molecules. You've got to get that right. Make sure that you don't get confused and you don't think of intermolecular forces as something happening between atoms. It's not between atoms, it's between molecules. So let's pick up by applying our knowledge now by looking at some examples. So here goes for question number 1, which says, what we're asked to do is to identify two things. We're asked to identify the type of bonding and intermolecular forces present in each of the following substances. So let's start. Number A, hydrogen sulfide. If we look at hydrogen sulfide, it has a chemical formula of H2S. The molecule looks like this, something like that. And what we need to recognize is that this molecule tends to be a little bit more linear than, I haven't drawn it entirely correctly, but what we need to recognize, it's not totally linear, but the forces of the electronegativity number difference here is actually quite small. So this is a very weak intermolecular, this is a small electronegativity number difference, and it tends to mean that this is not a very strong dipole. That is a very small plus, this is a very small minus, that's a very small plus on that side. So small electronegativity number, they're actually quite close to zero. Hydrogen sulfide is almost, in this sense, the bond is slightly, it's polar covalent, but it's not very strong polar covalent. And so what we will get is a weak dipole-dipole interaction. But we need to note that this is weak. The next one, which I'm going to do underneath so that we have got some more space, is water. Now water has a similar formula, H2O, and what we need to recognize and remember from the molecular shape section using VSEPR, you will recognize that it is something like a tetrahedral that's been squashed, so it's a bent molecule. But the oxygen here has two big lone pairs, and the lone pairs take up lots of space, and so the oxygen over here, it's electronegative, and it ends up being delta minus, where that becomes delta plus, and so it's a very strong dipole. So we'd say it's polar covalent. There is a difference, a bigger difference in electronegativity number, and this is a strong dipole-dipole. Dipole-dipole is what's going to happen, but we need to note that it's strong. And the second thing that we're going to need to note is that it involves when the molecules of water interact with each other, then what happens is that the interaction is between the hydrogen and the oxygen in that sort of a shape. And because it's involving hydrogen and it's strong, we give it a special name. We say this is a hydrogen bond. With water, if we look at water and we look at it in its different phases, which we'll come to, then you will recognize that water in its solid state, in ice, forms a particular geometrical shape. It forms six-sided rings. And it does that because of these strong hydrogen bonds. And so those are much stronger than the interaction between hydrogen sulfide. Even though hydrogen sulfide, the sulfur, if you look on the periodic table, you'll take a look and see that sulfur is below oxygen, and so sulfur has a higher mass than oxygen. You might expect the sulfur to have stronger forces, to have a better way of binding together, but it's not the case. It's because of this unique property of the shape of the molecule, of the water molecule, that it makes water have hydrogen bonds. And it's a very important distinguishing factor that you need to know, because they often ask that in exams. You'll see there's even a question later about that very same thing. Now, let's identify iodine. Iodine. Iodine is an element, but iodine is I2. So the minute you see that, what you recognize is there must be equal sharing. And when you get equal sharing, that means it's non-polar. Covalent bond. So the bond is non-polar covalent. The molecule is a non-polar interaction. It's not a dipole. It's going to be an induced dipole. If you want to, you could say induced dipole with an induced dipole. The example that we're going to call this type of force is London forces. It's an example of London forces. Now, these aren't very strong. Iodine, as a crystal, sublimes at about 35, 36 degrees. That means it changes from its solid state into a gas state because the molecules can't hold on to each other strongly enough to form a liquid. So they go straight from being a solid straight to a gas. And the indication that that is going to happen is a clear indication that the intermolecular forces are not very strong. Let's look at the final one. Final one is methane. And we did this one in our earlier section, just to revise. The interaction, the bond is between carbon and hydrogen. This is a polar covalent bond. But because of the symmetry, it's a symmetrical molecule. And because of the symmetrical nature of this molecule, the interaction between molecules of methane, of CH4 and another CH4, this is going to be very weak. The interaction here is nonpolar. Hope you've got that. See the difference between intra and inter. Intra, inside the molecule. Overlapping orbitals, sharing of electrons. Covalent bonding. Are the electrons shared equally or unequally? If they're shared equally, you've got a nonpolar molecule. If they're shared unequally, the bond is polar. If the molecule is symmetrical, then the molecule will be nonpolar. If the molecule is not symmetrical, the bond will be polar and the molecule will be polar. Form a dipole. Dipole, dipole, and all the others follow. So I hope you can see that once you've got it and you understand how to work out what is polar, what is non-polar, then you'll be fine. So here's a short tip, just to keep that in your head. If it is between a non-metal and the same non-metal, then in most cases, in every case, if this is the same, then you can definitely say that this is going to be non-polar bond. If it is a different non-metal, so non-metal metal 1 and non-metal 2, then you have to look at the electronegativity number difference, which you've done previously, and if it's above, if it's greater than 0,4, then you can say that this could be polar covalent. It's not always going to happen like that. The bond will be polar covalent. But if we say that we've got hydrogen and a non-metal, then in almost every case we can definitely say that this is a polar covalent bond, because hydrogen is such a small molecule. It's a small atom at least. Hydrogen is a small atom and it bonds with a non-metal. It ends up losing its electron quite easily. And that's one of the factors that ends up when we have a non-symmetrical molecule forming hydrogen bonds as well. So bear those things in mind. Hope you've got a summary in your head. Right, let's move on. Let's talk about states of matter. Now, from work that you've done earlier, you will recognize that we have solids, We have liquids and we have gases. And you would recognize as well from theory that we've done previously on the kinetic model of matter that molecules or particles of matter are in movement all the time. And these particles move around, they collide with each other depending on the distance between them and the forces. So let's just assume for the moment that we've got the same stuff and we're going to look at it at different temperatures. So we're going to look at a particular material, particular substance in its different phases. And I want to just illustrate that for you. So this is an unknown type of material, and we're going to just make it very easy to follow so that you've got a set idea here. If this is a window into a container, and we're looking at molecules of this particular substance, then we would say, as a solid, what would we expect? We'd expect the particles, the molecules, to be close together. And they'd probably be in some sort of ordered pattern. Okay? So I'm just going to sketch them like that. They're arranged quite neatly. Now, the question is, what keeps them in that pattern? These are molecules, remember, we're not talking about metals or anything else. We're talking about molecules. We're saying, what keeps these molecules in this pattern? Well, it's the intermolecular forces. At this particular stage, the particles are close enough together so that the forces are strong enough to hold them in a particular shape. The particles, the molecules here, are still vibrating. They are still moving, but they're moving very slowly because the temperature is very low. So I'm going to say temperature low. Now, what can we say? We can say here, stronger forces. These intermolecular, there are strong intermolecular forces. Guys, this doesn't matter whether we're talking about London forces or we're talking about dipole, van der Waals forces, or if we're talking about hydrogen bonding. When it's a solid, we can say they're strong. Even if at this particular temperature is low, it's strong. Those particles are close together. But what you need to recognize is just like gravity, there is a relationship between the strength of the force and the distance between the molecules. And it's even worse in intermolecular forces. The further you get away, the weaker the force. The forces are over a very, very short distance. You might remember that in gravity, when we're dealing with Newton's law of universal gravity, and when you deal with Coulomb's law, you'll say that the force is directly proportional to 1 over r squared. Over here, in London forces and in some of the van der Waals forces, it is as much the force is directly proportional to 1 over r to the 4 or r to the 5 or even r to the 9. They're very, very short distances. And so you need to recognize that although these molecules are very close together, they're held at a low temperature because they haven't got much movement. What happens when we increase the temperature? When we make the temperature a little bit higher, now we're only going to take a look at the same size or the same space, and we're going to have the same molecules. Now the molecules are freer to move. They're not in such an ordered pattern. And in fact, what we would say is they're able to slip over each other. They're not totally free. They haven't moved far away from each other, but they're still within proximity, but they're able to move around. They're not held in as fixed position because they've got more energy and they need to move. We need to understand that. What happens in a gas? So let's just say the temperature here is increased. Temperature is higher. And what we recognize is the forces here are still of the same nature, But because the molecules are further apart, the strength of the forces is going to be strong when they're close together. So this force is still going to be quite strong. But because the distance here is further, what we'd say is there's a less of attraction. So here we recognize there is less effect, weaker attraction. Weaker attraction because the molecules are further away. They are further away from each other. If we looked at a gas, we recognize in any gas, a gas takes the shape of the container and those molecules spread out. We would see them zigzagging all over the place, and if we took that view, that'd be far away. So the attraction, the strength of the forces between the molecules would be very weak. So this would be it would be very high temp, a very high temperature, very high, sorry, temperature. And what we're going to say here is the forces here have become much, much weaker. Very weak forces. They're the same type of forces, but understand that because they're now further away, they are very weak. They're examples of very weak forces. So this is crucial to understand. Although we've generalized and said hydrogen bonds are the strongest type of intermolecular forces, if we're dealing with a substance that's a gas, say like water, if you've boiled water and the water is changed into water vapor and it's gone into the air, then the forces between the water molecules, the potential for those forces to be strong is still there. But because the molecules are far away and they're moving with greater speed, remember that the temperature is directly related to the average kinetic energy of each of the molecules. So we've got that sense that these molecules now are moving faster, the forces are weaker, and that's the situation. So what we need to do is to be able to explain, if we change the temperature, what keeps the molecules in their state. The stronger the forces are to begin with, the more likely the temperature that a phase change will happen will be less. So if we take, for example, water, even though it's a small molecule with a low molecular mass, if we heat it up, it takes a long time compared to other things of a similar nature to change from a solid to a liquid to a gas. It has a higher melting point than we would expect. Soon as we see a higher melting point than we expect, we can say, that's an example of very strong intermolecular forces. There are hydrogen bonds present there. So if we looked at ammonia and hydrogen fluoride and some of the organic molecules, when we get an unusually high melting point or boiling point, we can say, reason, intermolecular forces. Okay, hope you've got that. Now, what else can we tell about intermolecular forces? Well, they influence, as I've just said, the melting point. If the melting point of a substance is low, so remember what melting point is. It's the temperature where we get a change from solid to liquid. And for a pure substance, that's a fixed temperature. So every pure substance has a certain temperature that it melts at. And the reason for that being consistent is that the forces between the substances, between the molecules, are uniform. They don't change from one day to the next. So if a substance has a low temperature, low melting point, so if we've got a low melting point, that means that you've got weak intermolecular forces. Where if you've got a high melting point, then that means that you've got stronger forces. Make sure you follow this. We can look at the physical properties of substances and try and explain them in terms of intermolecular forces. And you need to be able to do that. Boiling point is a similar problem, and it's a similar sense. Just to remind you, we could give you boiling point. Boiling point is the temperature at which liquid, all the liquid, changes to gas. In other words, nothing will remain. The temperature can't increase. So if we've got a very high boiling point, that's saying things want to stay as a liquid. That means that the forces are high. Are strong, at least not high. Let's just change that to strong. Forces are strong. When we're talking about these forces, we're talking about intermolecular forces. A third physical property that's also an important aspect of being able to interpret what's happening as we look at substances is density. Density is the ratio. It's the ratio of mass divided by mass and volume. So the formula that you will have seen earlier, probably in lower grades, is density is mass divided by volume. Very interesting thing. The density of substances, of pure substances, again, a fixed value. Aluminium, for example, has a certain density. It will always have a certain density. Gold will have a different density. How do we know this? Well, it's been used over the years to actually determine the purity of substances. The more pure substance, the closer it is to that substance's density. If you mix different metals together, you will find that the density changes. And so what we need to recognize here is that if we've got a high density, what's that telling us? It means that there's more mass, more atoms, more molecules in a certain volume. So if there's a higher density, more molecules, more mass in that certain, if we take the volume as being 1, more of it crammed into that. What's that telling you about the forces? High density means strong intermolecular forces. Now, this is critical. Intermolecular forces were discovered because of properties like density, like deviations in gases, in their behavior, when they changed from solid to liquid to gas, or from gas and they condensed to form liquids, and the liquids then changed to form gases, solids. These were the reasons that people came up with, that there must be forces between the molecules. We need to understand them and interpret them. So we've got a clear picture of what's happening in between the molecules. Right, let's apply our knowledge now to a question. Second question for today, and let's see how we can get through this one. The boiling points for 4 chemical substances are given below. We've got these, we've looked at them before. Hydrogen sulfide, minus 60 degrees. Ammonia is at minus 33. Hydrogen fluoride at 20, and water at 100. Now, what we've asked to do is which one of the substances exhibits the strongest intermolecular strongest forces of attraction between its molecules in the liquid state. Now, notice this is boiling point. This is the change, when you're looking at boiling point, it's the change from liquid to gas. And the one that has the strongest forces is going to have the highest temperature, of the highest boiling point temperature. And so water is the one that has the strongest intermolecular forces. Notice that hydrogen fluoride is the next one. And then if we look further down the list, you'll see that you've got ammonia and then hydrogen sulfide with the weakest intermolecular forces. You need to understand, by interpreting the position of the boiling point, the lower it is, the weaker the forces. Okay, next one. Give the name of the forces responsible for the relatively high boiling points of ammonia and water, and explain how this force originates. Now, guys, when we look at ammonia and water, what we need to recognize is the molecules aren't symmetrical. They are very strong dipoles, and they form hydrogen bonds. In both these cases, they're examples of hydrogen bonds. Water and ammonia, and to a certain extent, hydrogen fluoride, don't follow the trend. If we had to take molecules of a similar mass, we would find they have a much lower boiling point. If we looked at the melting points, they'd have a much lower melting point as well. And that's what they're meaning about relatively high, because it's due to the fact that there are hydrogen bonds present. Hydrogen bonds because they're very strong dipoles and because it's formed between the hydrogen. Now, the shape of hydrogen sulfide and water are similar, yet their boiling points are there's a difference. We have mentioned this. It's all about the intermolecular forces. Even though hydrogen sulfide has a larger mass, but it has a lower boiling point. I'm just going to abbreviate boiling point. Why is that? Water, and the answer is simple, water has hydrogen bonds. Even though water has a smaller molecular mass, normally what we expect, the bigger the mass, the more chance for intermolecular forces. Bigger surface area, more chance for them to interact. Here we recognize water has a much higher. Why? Because the link between hydrogen and oxygen is so much stronger dipole. It's more polar bond. The molecule forms a stronger dipole. Okay, I think we're moving into our last little property, and that is properties of liquids. Now, guys, here are some amazing things that you can investigate, and I'm just going to mention a few of them. First thing to recognize is that some liquids have an incredibly high surface tension. Water is one of those. It allows objects to move across it. You can float a pin on water. The reason is that the top layer of molecules forms a skin that are held together by those very strong hydrogen bonds. We also recognize some objects evaporate easier than others. So, for example, if I put ether down or a perfume down in a beaker and I allow it to move, what you'll find is that it will easily diffuse through the room and you'll smell it. Why? What's happened? The molecules in the liquid weren't strongly held together. Because they weren't strongly held together, they were allowed to move from being liquid into the gas phase. Evaporation is a key thing that you need to understand. You'll be dealing with that a little later when we talk about saturated vapor pressures and all that sort of thing. We're not going to do it right now. But evaporation, the more quickly something evaporates, it's an indication of the strength of intermolecular forces. A third aspect of liquids is what we call the capillary effect, or effect. The capillary effect simply means this. If you put a thin glass tube into a liquid, some liquids are able to climb that glass tube because the molecules have forces of adhesion and cohesion. Water is a very good example of cohesion. It sticks together. to form droplets. You put a little tube into water, you'll see the water molecules rising up in the tube. It's called the capillary effect. There is a last aspect of liquids and intermolecular forces that I want you just to think about, and I've got a little problem for you to deal with. And that is when we put stuff into a liquid, sometimes it dissolves and sometimes it doesn't. And how can we explain that? We can explain it by looking at the intermolecular forces. If the intermolecular forces are similar, then what we'll find is dissolving takes place. But the intermolecular forces are not similar, then what we'll find is there'll be no dissolving. Let's have a look at our problem. Right, question number 3. Look what it says. Describe the intermolecular forces present in each of the following solutions. So all we're looking at is describing what type of forces. We know that in water there are hydrogen bonds. And in ethanol, we find that ethanol has a structure that looks something like this, OH, and the rest are hydrogens. Now, the OH over there has the tendency to produce a negative on the oxygen. The oxygen is more electronegative than the carbon or the hydrogen, so this end becomes slightly negative, that end becomes slightly positive, and this becomes slightly positive. So there's a little bit of a dipole forming there. The intermolecular forces in ethanol are dipole-dipole. They're van der Waals forces. Dipole-dipole, and we could say van der Waal. And so as a result, there isn't too much disagreement between water and ethanol. Particularly if you put only a little bit of ethanol in a lot of water, the water is strong enough to break apart the intermolecular forces in alcohol. If you do it the other way around, you might find the water molecules joining together, and that does sometimes happen. Let's have a look at the next one, and I'm going to do it down at the bottom. If we take some sodium chloride. Now, sodium chloride is an ionic material, so it has sodium ions and it has chloride ions. And what are we going to find? We're going to find that the water molecules are going to come around it, and they're going to sit in different ways as I drew earlier. So what sort of intermolecular forces are we going to get? We're going to get ion dipole. Now, if we use the same number of molecules of water as ions of sodium chloride, the sodium chloride will laugh at the water. But if we put lots more water in, then again, the water molecules can surround the ions in the lattice, pull it apart, and we will get dissolving. So if we've got lots of water, it will dissolve, because the dipole-dipole forces, the ion dipole forces, will be stronger than the ion-ion forces. Right, what about this one? Carbon dioxide and water. Now, carbon dioxide is a nonpolar molecule. It is dry ice. It sublimes. They're generally weak. So this is nonpolar. And in water, we've already said it's hydrogen bonds. They are strong dipoles. So what are we going to get? We're going to get nonpolar dipoles interacting. And in this case, what tends to happen is if the nature of the interactions are not similar, then water tends to group with water, and the nonpolar substances tend to group with nonpolar. And how do we know that that is in fact what happens? Well, you know that carbon dioxide can dissolve in water, but it also fizzes and forms bubbles and releases from water. So in this case, we're just describing those situations. But what about ammonia and water? Well, ammonia, NH3, is dipole-dipole, and water, H2O, is dipole-dipole, and they're very strong. So we said these are hydrogen bonds between these. If we put them together, they both have hydrogen bonds. We're just simply going to get dipole-dipole, and that's what we were asked. We're not going to get anything different. And for this reason, if you take ammonia and put it into water, bubble ammonia, it will dissolve very rapidly. Huge, it's very, very soluble in water. Okay, guys, I hope that we've covered at least an overview, an introduction to intermolecular forces, and that you will have something to think about as you deal with this very important section. It will continue with you for the rest of your chemistry. Please make sure that you think about it all the time. And good luck as you try and interpret the physical properties in relation to what the intermolecular forces are in the given substances. From me, bye.